some of the elements of that space. Sumitra, did you start recording?
Yes, I have started.
Okay, thank you. When I was a student and I had this course on linear algebra, one of my problems was that it seemed that some proofs are like magic. Why this happens? And why, for example, diagonalization work? Why do we have Jordan formula? Because at the very beginning, they do not give a good explanation. They just show you it works. Go ahead, do the calculation, it works. And you want to understand why it works. And to do it right, here is the book. You see it. Linear algebra done right. So I strongly suggest to read this book and use it for any concept of linear algebra. And also some of them we need it here in this book.
Thank you. I really appreciate that, those comments. And I think one reason that you probably like it, as me, is it was written by someone who does functional analysis. Linear algebra is the study of finite dimensional vector spaces. But if you sort of know what's going to come in the next course, when you get to functional analysis, you write from a different viewpoint. And I think that's what helps this book particularly appeal to analysts.
Sure. Thank you, for writing this book, indeed, for us.
Thank you so much.
Yeah. So I go back to OneNote, start sharing. Okay, here we go. We saw that K of X y equal to mean of xy. It creates an RKHS, and let's detect some of its elements. And I mentioned application in economics. You'll see why economic is relevant here. Little k index y at point x, by definition, is k, x, and y. And here is the argument is x. And you see, if x is small, this is equal to x. And when x gets bigger, it's fixed. So the diagram of ky is like this. And at point y, it becomes constant. Our argument is x. And elements of W are linear combinations of this. So an arbitrary f in W can be written as sum a from 1 up to n, ai, k, o, y, I. And we can imagine what is easily now, what is the f of x, or what is the diagram of f of x. So it's n of these diagrams multiplied by different coefficients ai, and then you sum them up. Another way to look is, as before, without laws of generality, assume that y1 is less than y2, less than yn. And if your x is in between 0 and y1, the first interval, f of x, for all the function here, we are here. In other words, ki of x is equal to x for all of them. So we obtain sum from a from 1 up to n ai times x. It's a multiple of x. But when we pass to the second sub-interval between y1 and y2, f of x, the first function is already a constant, is a1, y1. But for the other, for the n-1 remaining function, we are in this definition of k, in this part of the definition. So it becomes sum I from 2 up to the n ai x. And it continues like this. We go from one interval to another, one term becomes fixed, and our coefficient changes. Each time we lose one element from the sum, and at the end, when x is bigger than or equal to yn, the last infinite interval, f of x is uniformly constant, absolutely constant, I from 1 up to n, ai, yi. And a is a coefficient. It can be even a complex number. But if you consider real number, the summation here, I mean, each of these sums could be negative or positive. So at the end of the day, what we obtain is something like this, and eventually constant. Between each interval, it's a multiple of x and eventually a constant. And on the slope of these lines, there is no restriction. Of course, based on the reasoning I gave, any function of this form has a diagram like that, and you can go backward. Start with any diagram like this, and you immediately see what is your y1, y2, up to yn. So this is y1, this is the last one, yn. The diagram tells you what are the points, and also the slopes are given, because here, the last slope, I didn't write here, when we are between yn and yn minus 1. F of x is equal to a constant plus anx. So the last slope that we have here is a n. The previous one is an plus an minus 1. So we find an from here, then an minus 1 from there, and we go backward. And the last one here gives us a1. Not that I don't say this slope is equal to a1, but I say that when we go backward, we obtain this last slope. So therefore, all functions of this form of a w. W is a piecewise linear function which is eventually constant. But still, we cannot tell what is w bar, which is over h. That needs more attention, and it's not in this part of the course. I mean, later on, we will not cover it because it's in the second part of the book. My goal is go up to chapter 6, hopefully, but there are many more chapters, and in one of them, this is studied if you are interested. The next example is RKHS induced by a positive matrix. So RKHS induced by p bigger than or equal to 0. P is an n times n positive matrix. It's written, but there is a reason I repeat it here. So P acts on Cn. We can look at it as an operator. And last week, there was a question that if you have already an infinite matrix which acts on L2 as a bounded operator and has further properties, for example, that is a compact operator or something else, other properties of operators. And we use this construction of Moore, we obtain an H. what can we say about H? So this is a partial answer to that question, because we start with a matrix P, which is positive, and we construct H using more construction. But the same idea can work in infinitely many, in infinite dimensional case, and you can see what happens. But let's do the simple case n by n, then it can be generalized. We have seen this before. What is Cn? Most of the time we can say that Cn is the set of vectors of dimension n, and we think of elements of Cn as vectors like this, sometimes vertical vectors. It depends on the context. But another point of view, which I already use, is to consider the set X, 1, 2, 3, up to n, and look at X as a function on X with element in C, such that X at point 1 is the first component, and at point n is the nth component. With this point of view, we can look at P, this n by n positive matrix. We can look at P as a function of x times x with values at C. P at point ij, as before, is nothing but the element in row I and column j. So that's the way we can look at it. And positivity is precisely what we need here. P bigger than or equal to 0 is precisely what we ask for the definition of a kernel function. So this creates a space H. So by more, there is H. You can call it H created by P. And we want to see what is this P, and obtain some description of some of its elements. So two things: what is H, and also what is the inner product in H, to be able to treat its elements. The first thing, it comes out of this. The kernel, which I wrote Pij, let me use our old notation. Let me write K for the kernel. What is the kernel function, little k? So little k is a function defined on X with values at C. The original definition is like this: Kj on the variable I is defined to be the capital K, I and G. And we know that this is Pig for any I. If you look carefully, this precisely means that Kg is equal to the j's column of P. So in other words, our kernel functions are precisely these columns of P. So this is K1, this is K2, and this is Kn, with this new interpretation. And W is the span of these kernel functions. And you see immediately this is equal to the range of P. And we are in the finite dimensional case. It's already closed, and that would be our space, H of P here, or H of K, if you want to call it, is nothing but the range of P. So the columns of P create a space, and this is the space which Moore gives us. But still, we do not know what is the inner product. For example, what is the inner product of these two elements? Not in Cn, in H of K. It's not necessarily the same. So what is the clue for that? So in other words, if F and G, or I mean U and W, whatever you want to call it, here it's better not to use F and, yeah, why not F and G? See, F and G is in H of P, then the question is, what is the inner product of F and G in H of K or H of P? Of course, they are vectors of dimension n, and we can do the inner product in Cn, but this is not necessarily the same as the other one. They are different. What is that? The clue is here. Well, every element of HP is a linear combination of these n elements. So in order to obtain the inner product, it's enough to find the inner product of two of these elements. So what is Kj? So this is, it's enough to say that what is Kj and Ki, but the inner product in H of P. What is this? Well, to do this observation, first note that by the meaning of inner product, this is Kj evaluated at point I. And we saw that this is, well, capital K-I-M-G or capital P-I-M-G, which is the element in row I, column G, is P-I-G. And now, crucial identity, to go back to inner product in Cn, I can write this as the, look, this is P, column G, row I. And that's the element which is here. I want to detect this element by an inner product in Cn. First, I do P times Eg. Eg are there, so let's mention En, canonical base in Cn. PEG means this column, and then inner product with EI in Cn. So I look at the beginning at the end. So summarize Kj, Ki in our space H is equal to PEJ and EI in Cn. It's not finalized yet, but that's a good start. We need to have something symmetric on the right side. Just have PEJ and EI is not symmetric. And the trick to do this is to note that when P or any other matrix which is positive, there is a square root of this. There is P half, which is also positive. That's another matrix which is positive. And p half times p half is equal to p. And so I can continue and write this equal to p half ej ei in Cn, and then take one of the p halves to the other side, noting that it's positive, so it's self-adjoint. So it's p half ej, p half, which one was ei? Ei is this one. Ei. This is good now. This is good now because now I have something symmetric. So kj inner product with ki in the space H is equal to the inner product of p half ej and p half ei in Cn. That's the crucial identity, which enables us to obtain the inner product of any two elements in H, because any two elements in H are linear combinations of kernel functions, and then expand and obtain this identity. Another thing that it helps us to do is to define an operator A from Cn to H of k by the following formula. I defined A of p half ej to be equal to kj. Well, there is an assumption before this. It's that P is invertible. If it's not invertible, I should say that it's from ranges. So temporarily assume that P equal to P minus 1. No, not exist. And then that is why the linear combination of all of this is equal to Cn. The formula I wrote here is equivalent to say that the main point is here, sum I from j from 1 up to n, a constant alpha j, p half ej is equal to sum alpha j kj. And the question is, as we witnessed before, why is this well defined? We can have a vector with different representation probably here. And the reason is this boxed formula. If you multiply by alpha I, alpha j, one of them bar, say alpha I bar, alpha j, and then sum from 1 to n over both I and both j, you obtain the isometry that I mentioned we needed. The vector here has the same norm as the vector there. And whenever we have the isometry, the definition is, this is the second time today that we face with this. So they have the same norm. So A is well defined. And this is a vector from, this is a matrix from Cn to H of k with this property. And with this, we can find the inner product of any two elements we want. There is, there is another, the property I just mentioned is this: for any V on W in Cn, the inner product of V and W in Cn using precisely this box formula, and the definition is equal to AV and AW in K. And it's very easy to prove this, because if V and W is in Cn, we can write V equal to a sum. The sum is alpha j, P a half Ej. Same for W, sum beta I P half EI. And now we calculate the left side, V inner product into W in Cn. It will be sum j from 1 to n, I from 1 to n, alpha j, beta I bar, P half Ej, P half EI in Cn. That's just expanding. And we know what is this. It's written here. P half Ej, P half EI, inner product in Cn is the same as the inner product of Kj, Ki in H. So this is so. Alpha j, beta I bar, Kj, Kr in the space K. And now we take the coefficient inside and add them up. J from 1 to n, alpha j, Kj, and sum I from 1 up to n, beta I, Ki. Okay. And this is precisely the definition of A of V. And this is A of W. Okay. So this establishes this formula, the inner product of V and W in Cn is the same as the inner product of AV and AW in K. That's one way to write it. But we wanted the other way around. In other words, we wanted to know the inner product between two elements in K. But now, since A is invertible, I mean, it's surjective and it's bijective indeed, we can call V prime to be AV in K and W prime to be AW in K. By invertibility, we obtain V and W. So immediately this implies that the inner product of V prime and W prime in K is A minus 1 V prime, A minus 1 W prime in C. That's the formula we were looking for. And we call that A was P half. It's even, I didn't mention this, but it's very easy in this case to see what is A. Recall that A is defined, I go back to the definition of A, by this formula. A applied to P half of Ej is equal to Kj. That was the defining property of A. On the other hand, we know that Kj is P applied to Ej. It's the J's column of P. And instead of Pej, I write it P half Ej. So we have two matrices, A and P half, and they coincide on these elements. But these elements, because P is invertible, they span of P half Ej is Cn. So this immediately implies that the A, which was unknown to us when we defined it, is indeed equal to the P half. And so A minus 1 is its inverse. And we can go back to our formula and say that the inner product of V prime and W prime in H is simply P minus half P prime, P minus half W prime, inner product in C. The formulas were easier in this case because we assume that P is invertible and we use it in several places. If not, there is a remedy, and we have a concept which is called pseudo-inverse. We can describe it this way. It's P from here to here. Assume that this is the kernel. I write it N for 2. And even in the book, the authors were cautious to call it null space, not kernel, because we will mix with the other kernel that we have here. So if we consider the null space and its complement N plus, then in general, we know that the range of an operator P when we complement is N of P star. But in this case, P is equal to P star is N of P, because P is equal to P star. And when we take complement one more time, N of P complement is equal to range of P complement 2-wise in infinite dimensional setting. If you want to generalize this formula, you need to be careful. It's range of P bar, but here we do not need bar because everything is closed. I mean, we are in the finite dimensional case. And in the general setting, when N is not equal to 0, it's a space, we can confine ourselves to N perp, and the image you see is also a NP perp. So the image is also there. So the restriction. So this P, the red P that we consider is from N perp to N perp. It has an inverse. It's bijective between these two. It has an inverse P minus 1. It's not on the whole space. It's from N perp to N perp. But they define an operator like this. P DAG is equal to P minus 1 on N perp, as we defined here, and on its complement equal to 0. In other words, everything here is mapped to 0. It's a kind of generalized inverse or pseudo inverse. It has some PDAG here has some properties of the inverse function, and everything I did up to here, you can do it and obtain results with P perp. For example, this box formula, which was interesting for us in the previous case, the product of V prime and W prime. Let me write it again. V prime and W prime in K, if P is invertible, we have this symmetric formula. It's in Cn minus half. I can take one of these P minus half to the other side. For example, I put it there. It becomes P minus half, P minus half, V prime W prime in Cn. So it's P minus 1 V prime W prime in Cn. Of course, you can put it on the other one too. So a formula that we have is inner product of any two element in K is the corresponding inner product in Cn but you put P minus 1 in front of one of them, either here or there. That's for the case we saw before. And if P is not invertible, the same formula works, except that instead of P minus 1, you write P DAG, the P that we have here. So for any P positive, invertible or not, the inner product of two elements in H is P DAG V prime W prime, or P DAG comes in like this. So that's why it's called a generalized inverse or pseudo inverse. It helps us to obtain a formula for the inner product in those cases. So anything else here? No, it finishes this part. I didn't write what happens in the infinite dimensional case, but the same formulas work, except that I mentioned at which point you need to be careful. It's precisely here. When you go to infinite dimensional case, NP perp is RP bar. So it's for infinite dimensional. Case, but it's still the generalized inverse works, and you can obtain formulas like this on L2 when a matrix, a positive matrix is given. Well, one last example that we need to treat and finish chapter 2 is indeed an interesting one about any Hilbert space. And it is more interesting if you consider Lebesgue spaces. For example, L2 of 0, 1. Of course, it's a Hilbert space. But when a function is in a L2, you cannot talk about the evaluation at a point, because a function in Lebesgue space is a ghost of a function. It's a family of the function, and we use a representative. It's defined almost everywhere. So at no point we can talk about the values of F. So we have a Hilbert space, but in a sense, we do not have an RKHS. We do not have a reproducing kernel Hilbert space because we cannot simply talk about the values of F. That's true. Even if you look at the first chapter of the book, among all the examples given, there is a section called a non-example. And a non-example is precisely this one, that in Lebesgue spaces, we cannot talk about evaluation. But still there is a remedy. And the remedy is that is this section. Any Hilbert space which is given, we can somehow transform it to an RKHS. Not necessarily on the initial set, but on something else. But still with the same inner product structure that I will describe. First, the definition of Gramian, probably we have seen this before. So H is a Hilbert space with inner product this one. Assume that H1 up to Hn are elements of the Hilbert space H. And you form the matrix inner product of Hi and Hj n by n matrix. This is called the gramian of these vectors. Gramian of H1 up to Hn. The way it's defined here, it's the matrix. In some books, the determinant is called the gramian, and even in some books, they even mention the determinant gramian. So you need to be careful which text you use. For us, it's the matrix here. And the simple lemma is that the gramian is always positive. So lemma. For any H1 up to Hn, but let me give a notation to this. Let me call it G, or if I want to mention its elements, G of H1 up to Hn, G of H1 up to Hn is always bigger than or equal to 0. And moreover, G is strictly positive if and only if H1 up to Hn are independent. The proof is very straightforward. We can see the yn in Cn, n elements, and ask what is G of y and y. Well, we know what it is sum over I and j. The coefficients, here are the coefficients, y. It's better to call them alpha. I don't know why it called it y. Okay. Alpha I bar, alpha j, and gij, the element in row I and column j in matrix capital G. So it's sum let's write it as well. Sum A from 1 up to n, j from 1 to n, alpha I bar, alpha j, and this is Hi in a product with Hj in the space H. And take the coefficients inside and sum them up. It's sum I from 1 to n, alpha I bar Hi, sum j from 1 to n, alpha j bar Hj, which is the norm squared. And this is bigger than or equal to 0. As you see all the time, I kept bar over alpha I, and here I end up with alpha I bar Hi, so it sounds to put bar on alpha j, but it really doesn't matter, and this happens many, many times. One thing this shows is that G is positive, G of y is always positive, so that's the meaning of being positive. And moreover, G of y and y is equal to 0 if and only if sum I from 1 to n alpha I bar h is equal to 0, and this is in H. And strictly bigger than 0 means that this combination, if y, what does, let's recall what does g strictly bigger than 0 mean. This is equivalent to say that if y is not identically 0, g of y, like this, is strictly bigger than 0. Strictly bigger than 0. And we see that this happens if and only if for any y equal to 0, sum of alpha I bar hi is not equal to 0. In other words, hi, h1 up to hn be independent. We call that these are the coefficients of y. Okay, so now I will continue after the break. We have G, which is positive. So Moore theorem tells us that there is an RKHS. So G positive. G positive, so by Moore. There is an H, which we can say H of G. So now we want to see what is this H of G. And this will also answer the question which was asked before the first break, because when we have conjugate, we will see it here again. In a sense, H of G is the same as H, but the inner product is conjugated. We will see after the break.